Hello and welcome to Chapter 8. So in this first section, we're continuing on with our hypothesis testing, but we're just dealing with different scenarios. So in this chapter, we're dealing with things with two samples. So rather than just giving you one sample mean, one sample standard deviation, now we're going to give you two. So before we start, I want to define two new things. So these are words that you've seen before back in our probability chapter, but now we're dealing with them in terms of samples instead. So that's the independent and dependent samples. So independent just means that the sample selected comes from a population that has nothing to do with the other sample. So not related to the second sample at all. And so the dependent samples is basically the opposite. So in dependent samples, each member of one sample corresponds to a member of the other sample. And the easiest way to explain that is through example. So in this first one, it says classify the pair of examples as independent or dependent. So sample 1 says that weights of 65 college students before their freshman year begins. So I don't know if you guys know about the freshman 15. When you're in your freshman year of college, if you're living in the dorms, a lot of the dorms have food that's pretty much readily available to you all the time. Like I went to a college where my meal plan was basically I had like 200 meals for the quarter or whatever, and then every meal I could eat as much as I wanted. So it was super easy to gain weight because it was basically a buffet for every meal. So here in the study, sample 1, they're looking at the weights of 65 college students before their freshman year begins, and then for sample 2, they're looking at the weights of the same 65 college students after their freshman year. So because it's the same 65 college students, each member of one sample corresponds to a member of the other sample. So these 65 students and these 65 students are exactly the same people. So that's why this counts as dependent. My second example, I have scores for 38 adult males on some psychological screening test for ADHD. And then for sample 2, I have scores for 50 adult females. So because these are different people, they obviously can't be the same people, then that makes it independent. Okay, so if we are writing our hypotheses for hypothesis testing with two samples, we're still doing the same process. We just have our hypotheses are going to look a little bit different. So for our null hypothesis, our HO, because we have two samples, that means we're going to have two means. So we're going to have mu1 and mu2 to talk about our two different samples. So this is the mean from the first sample, mean from the second sample. And remember with this one, this is your population mean, so this is basically what's being claimed in the problem. And so with the symbols in between our two means, it's still going to be the same symbols that we're using from before. So we can choose between the equal sign, the less than or equal to, or the greater than or equal to. Same symbols as before. Our alternative hypothesis, our HA, will basically be the same. mu1, mu2. And so it's the same opposite symbols as we used from before. So if it's an equal sign in our null hypothesis, it'll be does not equal for our alternative hypothesis. If it's less than or equal to for our null hypothesis, then it'll be the opposite, so it'll be greater than. And if it's greater than or equal to, then it'll be less than. So that part's the same as before, we just have two mu's. So that's what's changing. In our process, we always check our conditions first, and there's 4 to check for now. So you have to be given a population standard deviation for sample 1 and for sample 2. So you have to know those things before you can use this process. Then you have to make sure your samples are random, your samples have to be independent, and you either have to have the problem say that it's normally distributed for both samples, or both samples are greater than 30. So that's what you're checking for. Okay, So then when we calculate our test statistic, we're looking for like our z-score because we're trying to figure out our rejection region from it so that we can reject or fail to reject. So your formula looks like this. Sorry, mine has a small typo in it. So as long as you look at yours, it looks better than mine. So you guys have the right version. But you're just taking the two sample means. So remember on top, the x with a bar on top is your sample mean. And then the 1 and the 2 next to it just means whether it goes with your first sample or your second sample. And then underneath, we have a big square root. It's kind of like that standard deviation over the square root of n thing, but slightly different now. So we have here, it looks crazy because it's got sigma with a 2 on top and a 1 on the bottom. So this is just the standard deviation of your first sample squared. So let me write that out. SD from sample 1, and you're going to square it. That's all that is. And then you're going to do the same thing with your standard deviation of the second sample, square it. Each of those gets divided by its own sample size. Add them together and then square root the whole thing. So let's do this with numbers just to make sure we do this correctly. So in this example, we have a credit card watchdog group claims that there's a difference in the mean credit card debts of households in California and Illinois. The results of a random survey of 250 households from each state are shown below. The two samples are independent. Assume that the standard deviation for California is $1,045 and for Illinois it's $1,350. Do the results support the group's claim? Use alpha equals 0.05. So just like all of our other problems that we've done, we're going to check our conditions. So here we have 4. Our first one is just to check that both standard deviations for the populations are known. So we know our 1 is going to stand for California and 2 is going to stand for Illinois. So I'm just going to write that over there just to help me remember. So California standard deviation, they told us, was 1045. And our standard deviation for sample 2 was 1350 as given to us here. And there's another typo. Yay, that should say a 2. Okay, then second condition, the second rule that we need to follow is that the samples need to be random. This should be told to you, so that's what you're just looking for in the problem. And here it does say that they give us a random sample, or sorry, random survey. So that tells us that they chose random people for this. Okay, rule number 3 is that the samples have to be independent. So like we said earlier, the sample of one doesn't correspond with the sample of the other. So these two samples are from 2 different states, so they aren't the same people, should be fine. And they also told us samples are independent. And the check for number 4 is that it either has to say normally distributed in the problem or both the sample sizes have to be greater than 30. Well, they gave us that N1 and N2 are both 250. Both of those are bigger than 30. So we're good. Okay, all our conditions are met, so let's start writing our hypotheses. We have HOHA. Okay, so in the wording of this question, the claim says that the credit card watchdog group claims that there is a difference. So these are the key words right here. If there is a difference, they didn't say like how the difference goes, like if one is bigger than the other. So is a difference is just, is it equal to or is it not equal to? So if that's the case, HO is going to be the equal, HA is going to be the not equal. And that's it. Alpha, they told us to use 0.05. So then let's calculate our test statistic. So our formula, we're taking our sample means, the first one minus the second one. So I'm going to rewrite the formula just so it's easier to see what I'm filling in. So X bar 1 was the mean of California, which they told us was 4777. And then X bar 2 is the mean of Illinois, which was 4866. Divided by the square root. Giant square root. And then on the bottom we have the standard deviation squared from our first sample, which was our 1045. So I'm going to square that and then divide it by N1, which they told us was 250. Then I'm going to add that to standard deviation squared of the second sample, which was 1350. Okay, so when we do the calculations on top, if we subtract the 4777 minus the 4866, we get negative 89. On the bottom, when you do this in your calculator, you should get like 107.97 something something something. So if you're not getting that number, we might need to double check that. So finally, when you divide these two numbers, you should get negative 0.82. So that's going to be our test statistic, our z-score. Okay, so again, you want to double check that in your calculator, make sure you can get those numbers and type them in correctly to get your final number. Then moving on to our p-value rejection region. So I'm going to draw the picture first. This is the same thing that we've been doing. Nothing new here. Same thing with the decision. It's going to sound exactly the same as what we've been writing. So for our rejection region, we are doing a two-sided test because of our HA is does not equal. So I'm just going to go ahead and shade both sides right now because of the does not equal. Alpha equals 0.05. That means in each of these shaded regions, I should have 0.05 in it. And so because I have two of them, I'm going to divide it by 2. So alpha divided by 2 gives me 0.025. And that means over here is also alpha divided by 2 is 0.025. So that means there's 2.5% in that shaded region there, 2.5% in that shaded region there. So when I find my z-scores in the chart, I'm looking for 0.025. And from doing that, you should get negative 1.96. Which means the other side will be positive 1.96. Okay, so basically, if our test statistic falls in either of those shaded regions, then we get to reject because that's our rejection region. But negative 0.82 is actually, well, 0's in the middle, so negative 0.82 is going to be like here-ish. So it does not fall in the shaded region, so this would be a fail to reject. Okay. So, knowing that, let's go to your decision. So it's going to sound the same as before. Our test statistic of negative 0.82 is less extreme than our rejection region. We fail to reject HO. And so we do not have evidence of our HA. Our HA said the two means are not equal. So I'm going to say that if they're not equal, that means there's a difference. There is a difference in the mean credit card debt, because I think that's what this problem was talking about. Credit card in California and Illinois. Cool. Okay, in my next example. So I have a similar setup here. I've written out my conditions already because they told us our two population standard deviations. They told us that there was a random survey, so that meets our random requirement. Our independence is given here. And then if you look at N1 and N2, we don't have numbers that are greater than 30. But in the problem itself, it did say that it was normally distributed. So everything checks out. We're good here. For our hypotheses, we got our HO and our HA. In this problem, I'm going to let Texas be sample number 1 and Virginia be sample number 2. So it says that the travel agency claims that the average daily cost of meals and lodging for vacationing in Texas is less than the average daily cost in Virginia. Well, if they're telling us less than does not have an equal sign in it, so that's how I know it's going to be an HA. So remember, HO is always the one that has the equal sign in it, so that means the HO will have to be greater than or equal to. Okay, so that's my hypotheses. Alpha is 0.01 given to us here, so let's calculate our test statistic. So here I have it set up. The Texas mean was 234, the Virginia mean was 240, divided by the big square root of my first standard deviation, which is 19. I'm going to square it over my N1, which was 25. Second standard deviation was 24. I'm going to square it and then divide it by N2, which is 20. From that, you should get, from the bottom, like 6.58-ish. I'll just put the ... Remember, keep your decimals in your calculator all the way until the very end. But when you divide this, you end up getting negative 0.91. Okay, so that's our test statistic. So when I draw out my p-value rejection region, my HA says it's less than, so that means I'm shading to the left. And because this is just that shaded portion, alpha is 0.01, so all of that has to be 0.01. If I look in my white chart here, looking for 0.01 in the middle, the z-score corresponding to that should be negative 2.33. And then comparing that with my test statistic, if 0 is in the middle, negative 0.91 is there. Again, it's not shaded, so this is failed to reject again. And our decision will be pretty much the same as before. So our test statistic of negative 0.91 is less extreme than our rejection region. We fail to reject HO, and we do not have evidence to support that the HA is true, meaning the mean cost of meals and lodging for vacationing in Texas is less than the daily cost in Virginia. So that would be my decision. That's it for 8.1. Good luck. Let me know if you have questions. I'm always on Microsoft Teams 8 through 11 a.m. every day.